Welcome to Summarize Science. Today we are looking at a fascinating paper titled SpatialEvo, which introduces a new way for AI to develop spatial intelligence. Spatial reasoning is the ability to understand how objects are positioned in a 3D world, which is a massive challenge for robots today. Usually, improving these models is slow because they require thousands of manual annotations from humans to learn correctly. The researchers point out that current AI training often relies on model consensus, where one AI checks another AI's work. The problem with this approach is that if one model has a bias or makes an error, the other models might just reinforce that mistake. SpatialEvo solves this by using something called a deterministic geometric environment, or DG. Think of the DG as a perfect math-based judge that doesn't guess, but calculates the truth using geometry. This diagram shows the spatial self-evolution loop, where the AI takes on two different roles. In one role, it acts as a questioner that looks at a scene and comes up with a challenging spatial question. In the other role, it acts as a solver that tries to find the precise answer to that question. Because the environment is based on actual 3D point clouds and camera poses, the system knows the exact right answer every time. The system covers 16 different categories of tasks, including measuring distances and identifying directions. For example, if the AI asks how far a fireplace is from a TV, the system calculates the nearest point distance mathematically. This replaces the need for human labels with objective, physical feedback from the world itself. This means every unannotated 3D scan of a room can suddenly become a high-quality training lesson for the AI. The researchers also included a task-adaptive scheduler to make the learning more efficient. Instead of just practicing easy things, this scheduler identifies exactly where the AI is weak and focuses training there. It is like a student who realizes they are bad at geometry and decides to spend more time on that specific subject until they master it. This creates a dynamic curriculum that gets harder as the model becomes smarter. When we look at the results, SpatialEvo outperformed all other major baselines across 9 different benchmarks. It achieved the highest average scores in both small-scale and large-scale model versions. Crucially, it improved its spatial skills without losing its general ability to understand images and text. This proves that focusing on 3D geometry doesn't distract the AI from other important tasks. This graph shows how the AI gradually shifts its focus toward more difficult categories like relative direction. At the beginning of training, it spends time on simpler things like room area estimation. As it masters the basics, the scheduler automatically pushes it to solve more complex 3D puzzles. This self-driven improvement is the key to creating truly independent spatial intelligence. Here we can see real examples of how the AI's descriptions became much more detailed over time. In the early steps, its observations were very brief and lacked a deep understanding of the scene. By the final steps, it could accurately localize objects and describe their positions relative to the camera with great detail. This visual progress shows the AI moving from simple recognition to true spatial awareness. To recap, SpatialEvo allows AI to use the laws of physics and math to teach itself 3D reasoning. By removing the need for human labels and model guessing, it creates a noise-free way to improve robots. In the future, this could mean household robots that never get lost and autonomous drones that navigate complex spaces perfectly. Thank you for watching Summarize Science, and we will see you in the next deep dive.